Okay. Damn it. Okay. So this talk is about testing distributed systems under partition faults. Despite many formal approaches like sophisticated verification techniques or systematic exploration like model checking, when it comes down to complex software like implementations of complicated distributed systems, practitioners tend to still just test their code. And often it's actually by providing random inputs. So academic wisdom sort of would tell us, well, there's no chance this is going to find anything. I mean, the probabilities are so astronomically small. No way you're going to find bugs this way. But despite our best judgments, it turns out random testing is surprisingly effective in finding bugs. So the point of this paper is to explore this unexpected effectiveness in this domain of testing distributed systems under partition faults. So to give you a piece of evidence of this effectiveness, there is a tool called Jepsen, which is a testing framework for black box testing of distributed systems under partition faults. The way this framework works is it allows you to set up a distributed system and run it on some number of nodes, like 5. And then it randomly partitions the network into 2 blocks and heals the network after a while and repeats this. And then you wait to see if things are going to break. And things do break, despite people designing their systems to be partition tolerant. Things do break, and the author of this framework found many bugs in many real-world systems like the ones listed here. So why does he find bugs with just a few iterations of this little loop here? To answer this question, I'm going to first set up an abstract framework, testing framework, which talks about abstract notions such as tests and testing goals and goal coverage. And then I'm going to cast the problem of testing distributed systems under partition faults in this framework to get our answer. And then I'm going to take a step back and view what we're doing in sort of a wider context of combinatorial testing. So let's start with the general testing framework. We're given 2 sets, a set of tests and a set of goals. And we have a notion of goal coverage. So a test may cover one or several goals. So if we execute all tests, they're going to cover all goals. But what we're interested in is achieving the full coverage with a smaller set of tests, preferably the smallest such set of tests. And the intuition is that we will call such tests that achieve full coverage covering families. And the intuition is that small covering families will lead to efficient testing. So now the goal becomes how to construct these small near-optimal or near-optimal covering families. And in this paper, our approach is probabilistic. So we have randomized constructions. Suppose we now equip the set of tests with a probabilistic distribution so that we can randomly select tests. And on the other hand, we fix some goal from the set of goals. Now suppose that there's a way to provide a lower bound on the probability that a random test covers a fixed goal. And this is going to be denoted by P. What we're going to do is characterize the sizes of covering families with respect to P and the number of goals. again, suppose we have our set of goals, and the probability that a random test covers a fixed goal is greater than or equal to p. I claim that there exists a covering family of size p, 1 over p times log g. And to show this theorem, we're going to use a technique from combinatorics that's called the probabilistic method. And this is a somewhat neat trick that uses nothing but school math, high school math, but it still provides you this existence. So I'm going to walk you through the proof. So we know that a random test covers a fixed goal with probability at least p. So the opposite, a random test does not cover a fixed goal, will be with a probability at most 1 minus p. Now suppose we sample k random tests independently. The probability that all of them do not cover this fixed goal will be at most 1 minus p to the power of k. And now we sum up over all goals to get that, and apply the union bound, to get that the probability that our k independent tests do not cover some goal, this will be upper bounded by the size of g times 1 minus p to the power of k. And now, if we take k to be equal to our desired size, we find that this probability is strictly less than 1. This requires a bit of math here, but trust me, so the probability is strictly less than 1. What that means is that the opposite, the probability of the opposite event, that our k-independent events tests form a covering family, will be positive, strictly positive. And that means, in particular, there exists some k tests that are a covering family. So this is, we've now shown existence in a purely non-constructive way of a family of size 1 over p times log g. We can tweak this argument to get a slightly stronger result, which tells us that by sampling just a few more tests, we can achieve that our family is a covering family with a probability arbitrarily close to 1. So with this, we have now our random testing framework. What we need to do is only say what are tests, what are testing goals, what is our notion of coverage, and then what is the bound on this probability. And we immediately get a randomized procedure to construct covering families with a high probability. So let's see how this works in this case of distributed systems under partition faults. But before I get to that, here's a puzzle. In a dojo in Kaiserslautern, N ninjas are in training, and they train in rounds. In each round, the ninjas split into 2 teams. We'll say that the training is complete if for every pair of ninjas, there is a round in which the 2 ninjas train in opposing teams. The question is, how many rounds do we need to make the training complete? So on this little example here, we have 4 ninjas and 2 rounds. The teams are depicted by these weapon icons. And if we just go through all pairs, we'll see that these 2 rounds suffice in this case. So for each pair, there is a round in which the 2 ninjas train in opposing teams. Right? So, of course, in general, 2 rounds will not suffice. In fact, since there's n squared pairs of ninjas, it is easy to see that n squared will be the upper bound. We can always just split 2 ninjas and then distribute the other ones arbitrarily. So we can finish the training after n square rounds. The question is, can we do it in something like log n rounds? So let's generalize the puzzle a little bit. Now there's n ninjas, and they're training in k teams. And training is complete if for every choice of k ninjas, there's a round in which all k train in different teams. Again, the question is, how many rounds do we need? Here we have 4 ninjas, and let's say k is 3. We have 3 teams. Again, we can convince ourselves that these 2 rounds suffice. They won't suffice in general. Again, n to the k is the naive upper bound. And the question is, can we do it in something of this form? So a function of k times log n rounds. So this is a puzzle. You can think about it completely independently of the rest of the talk. If you don't care about distributed systems, think about the puzzle. But there is a connection. So this actually is about testing distributed systems in disguise. And the connection is the following. So ninjas are nodes in a network. Teams are blocks in a partition. Rounds are partitions themselves. And the notion of the complete training will correspond to our notion of a covering family. So now let's go through our recipe. Let's say, precisely what are tests, what are goals, and what is the notion of coverage. So our tests are partitions into k blocks. Our testing goals are sets of k nodes, and our coverage notion is that a partition P covers a set S if it splits S, that is, it places each node from the set in its own block. And in this context, we call covering families splitting families. So why is this coverage notion interesting? To tell you that, I'll tell you about a bug found by Jepsen. And it has to do with this system called Chronos, which is a distributed job scheduler. So it allows you to, you can specify what are your jobs, when they should be executed, and they'll be executed in a cluster of n nodes. This system works in conjunction with another 2 systems called Mesos and Zookeeper. And there are 3 special nodes as the system is running: Chronos leader, Mesos leader, and a Zookeeper leader. We don't know if we're testing it as a black box which nodes these precisely are. So it turns out these are somehow important in the way the system maintains consistency. If at some point Chronos leader gets separated, gets cut off from Zookeeper leader, then interesting things start to happen. So in particular, the author of Jepsen, he reported this issue that if we separate Chronos leader from Zookeeper leader, this can cause the system to crash. And it crashes, completely abruptly, crashes the JVM. So he reported this, and then, the developers, being proud of their system, they said, well, this is actually an expected behavior, because this is actually a pessimistic way for the system to maintain consistency. So if it crashes, it cannot go wrong, right? So the author of Jepsen said, fine, okay, so now we know that if these 2 are separated, the system should crash, except that there are cases where it doesn't crash. So he goes there and makes another bug report. The system does not crash when these 2 get separated. And then they said, well, yeah, okay, this is a bug. Still not fixed. So here we see that this is actually an instance of splitting coverage, because we're trying to separate 2 nodes into two different blocks. So it's splitting coverage with the parameter k equal to 2. So let's do the last step there, bounding the probability of covering all goals. So to do that, we need to do a little bit of combinatorics. I'm not going to go into details, but just, you can see that the number of partitions with k blocks is a quantity called Stirling number of the second kind. This is roughly k to the n divided by k factorial. The number of sets of k nodes is n choose k. That's roughly n to the k divided by k factorial. And then we can see that the probability of splitting a set with a random partition is that quantity over there, roughly k factorial over k to the k. So now we plug in the numbers into our general theorem. We find that there exists a k-splitting family of size, well, the function of k times log n. So if k is a small constant, like 2, then we need to do exponentially fewer tests than the size of our system. And this basically explains why Jepsen is so effective in finding these kinds of bugs. If we go back to the more general theorem that tells us, talks about the probability of getting a splitting family, and we plug in the numbers like n is 5, we have 5 nodes, k is 2, we're splitting in 2 blocks, and we say epsilon is 0.2, we see that 10 randomly chosen partitions will provide full splitting, split every pair of nodes with probability 80%. So you see that just a few tests cover all goals here. So in the paper, we have other notions of coverage, like there's a KL separation where when we need to split 2 sets of K and L nodes. There is the minority isolation where we need to, where a node needs to end up in a smaller block to break some quorums and things like that. And in all these cases, the sizes of covering families are of the order of log n. So now there are basically 2 points I want to make here. So the first point is that these 3 cover most of the bugs found by Jepsen. The second thing is that, Jepsen doesn't know and doesn't care about our coverage notions. The test is just randomly partitioning the network, like one partition after another. So what happens is that after log n of these partitions, all these coverage notions will be simultaneously satisfied with a high probability, and therefore Jepsen finds these bugs quickly. Okay. So now let's take a step back and view what we're doing in a wider context. So we have our general testing framework. There's tests, there's testing goals, there's a notion of coverage, and now we need to show how to construct these optimal or near optimal covering families. In the case of distributed systems, for splitting coverage, our partitions are, our tests are partitions, our goals are sets, our coverage notion is splitting coverage, and our way of constructing covering families is a randomized construction that constructs families of size log n. There are other scenarios in which we can apply these kind of reasonings. So I'm also working on testing concurrent programs where I think of a program as a partially ordered set of events. Their tests are schedules, that is interleavings of events. Goals are ordered sets of k events. And the coverage notion is that a schedule hits an ordered set if it orders the events in the appropriate order. And here there are various constructions that we have for covering families called hitting families, in this case, of sizes log n to the k minus 1, n to the k minus 1, and so on, depending on what the underlying partial order actually looks like. Then in software engineering, there is this thing called combinatorial testing, where people provide inputs to their systems, and inputs they're structured inputs consisting of many features. And then what you want to do is, your goal is a particular choice of values for some choice of k features. And now your coverage notion is that the input coincides with your choice of values and features if it has those values for those features. And then people come up with various constructions for covering families there. They call them covering arrays in this setting. So yes, that's sort of a general framework. It can be applied in other scenarios. And now I'm going to finish and open the Q&A session with a question for you. So where else can we apply this approach? So thank you.
Questions?
I think this may be partially answered by your slides about concurrent testing, but a question about distributed testing distributed systems, is that just intuitively one would expect that the bug finding ability of a particular test would depend not only on the characteristics of the partitions, but on exactly when the partition happened.
That's true. There's a lot of, so this is a somewhat crude, model. The timing issues are sort of a bit pushed under the carpet, but there is actually in the paper we deal with it in a way. So the thing is that as the system is running, you also bombarded with requests, with like random requests. And then we sort of deal with the timing issue by saying that once the partition is started, then sort of the next operation that happens needs to be something for the bug to arise. And sort of then by just going over all possible next operations that happen right at that point, you also get similar kinds of results. But yes, in general, there's other kinds of tests the author of Jepsen is doing, and there's other kinds of bugs, performance bugs, that are completely out of the scope of this reasoning. And yeah, so.
Thank you.
Any more questions? Let's thank the speaker.